Today, Mars looks like a frozen graveyard, dust storms, silent craters, and endless desert. But the planet's surface hides a secret written in stone. Across this barren world are massive river valleys, ancient lake beds, and glaciers locked beneath layers of rust-colored dust. Billions of years ago, Mars may not have been dry at all. Water may have flowed across its plains, carving canyons, filling craters, and shaping landscapes that look strikingly familiar to Earth. Some scientists believe entire lakes once existed here, maybe even oceans. In this chapter, we follow the traces left behind: frozen water, buried ice, and the mysterious ancient lakes that reveal Mars was once a very different world. Beneath the surface of Mars lies an enormous store of frozen water, preserved in buried layers that stretch across much of the planet. Radar surveys from orbit have revealed subsurface ice only centimeters below the ground in some regions and meters deep in others, forming reservoirs that rival the size of Earth's largest glaciers. These hidden deposits record ancient climate cycles, times when Mars tilted more steeply on its axis, allowing snow and frost to accumulate far from the poles. Over millions of years, dust, sand, and volcanic ash buried these icy layers, insulating them from sunlight and keeping them remarkably stable in the planet's thin, cold atmosphere. Clues to this underground ice appear on the surface: fresh impact craters that expose bright, clean ice, polygonal ground patterns shaped by freeze-thaw stresses, and scalloped depressions where buried ice has slowly sublimated away. In higher latitudes, entire landscapes show textures that point to massive, buried glaciers creeping beneath protective debris. Understanding subsurface ice helps scientists reconstruct Mars' climate history and guides future exploration, since these frozen stores represent one of the most promising resources for sustaining human missions, providing water, oxygen, and even rocket fuel on the red planet. One of the most intriguing clues to Mars' watery past comes from a series of raised terraces and curving ridges that resemble ancient shorelines. These features encircle vast basins in the northern hemisphere, a region that many scientists believe once held a massive ocean billions of years ago. The terraces appear at consistent elevations over great distances, as if waves or tides repeatedly carved the landscape before the water eventually disappeared. Some shoreline-like ridges stretch for hundreds of kilometers, tracing the edges of what may have been an enormous, long-lived sea known as the Northern Ocean. High-resolution topographic data show flattened coastal plains, delta structures, and sediment deposits that further support the idea of standing bodies of water. In places where ancient rivers emptied into these basins, fan-shaped deposits resemble Earth's river deltas, hinting that flowing water once interacted with the shoreline environment. Although erosion and later volcanic activity have modified these landscapes, the overall patterns remain visible from orbit. By studying these possible ancient shorelines, scientists hope to determine how large Mars' oceans were, how long they persisted, and whether they could have provided habitable environments capable of supporting early microbial life. Some of the strongest evidence for long-lasting surface water on Mars comes from ancient river deltas preserved inside impact craters, including Jezero crater. These deltas formed when flowing rivers slowed abruptly as they entered a standing body of water, causing sand, silt, and clay to settle out and accumulate layer by layer. Over thousands to hundreds of thousands of years, and possibly longer, this steady deposition built broad, fan-shaped structures with precisely stacked sediment layers. Their shapes preserve clues of shifting river channels, changing shorelines, and fluctuating water levels, recording Mars' wetter past in remarkable detail. Orbital images reveal finely layered cliffs, branching channels, and terraces within these delta fans. On the ground, rover observations confirm minerals that form only in the presence of liquid water, strengthening the case for long-lived lakes. Delta sediments are especially important because fine-grained layers can trap and preserve organic molecules, shielding them from radiation and chemical breakdown. By studying these deposits, scientists can reconstruct ancient flow patterns, estimate lake depth and duration, and identify the most promising rocks for biosignature searches, materials that may still hold chemical traces of ancient microbial life preserved in Mars' sedimentary record. Clay minerals on Mars are among the most compelling indicators that the planet once hosted long-lasting bodies of water. These minerals form only when volcanic rock interacts with liquid water over extended periods, sometimes thousands or even millions of years. Their presence in ancient terrains across the highlands reveals that early Mars had stable water environments, with lakes, groundwater systems, and slow-moving streams altering the chemistry of the crust. Different types of clay tell different stories. Some formed in mildly alkaline waters, while others point to conditions closer to neutral pH, similar to freshwater on Earth. Orbital spectrometers have mapped broad deposits of greenish, iron and magnesium-rich clays, particularly in regions dating back more than 3.5 billion years. Erosion has exposed these layers in crater walls, valley slopes, and fractured bedrock, showing a rich geologic history shaped by water. Not only do clays preserve chemical fingerprints of their formation, they can also trap and protect organic molecules, making them prime targets in the search for signs of past life. By studying where clay minerals occur and how they are layered, scientists gain insight into the duration, chemistry, and habitability of ancient Martian water environments. Across Mars' mid-latitudes, several impact craters contain remarkably well-preserved deposits of water ice, protected for millions of years beneath thin layers of dust and debris. These ice-filled craters act like natural cold traps. Their steep, shaded walls reduce direct sunlight, and the planet's cold temperatures keep buried ice stable even outside the polar regions. Radar measurements from orbit have detected ice-rich deposits that can be tens to hundreds of meters thick in some locations, forming buried sheets of relatively clean material just below the surface. Much of this ice is thought to be a relic of ancient climate cycles, when changes in Mars' axial tilt shifted where ice could accumulate. During those periods, snowfall and frost may have built up in these craters, later becoming sealed beneath protective layers of sediment. Erosion and impacts sometimes expose fresh ice along crater walls or newly formed slopes, creating bright blue-white patches that stand out sharply against the red terrain. These exposures allow scientists to estimate the ice's purity, thickness, and how quickly it is slowly sublimating into the atmosphere. Many of these craters appear partially filled with frozen material, suggesting long-term stability on geological timescales. Studying ice-filled craters helps reconstruct Mars' climate history, track water movement across the planet, and identify accessible ice resources for future robotic missions, and eventually human exploration. Across Mars' mid-latitudes, the surface preserves compelling evidence that glaciers once flowed across the landscape. Although these glaciers are now frozen solid and often buried beneath layers of dust and rock, their signatures remain clearly etched into the terrain. Flow-shaped ridges, lobate debris aprons, and moraine-like accumulations form patterns strikingly similar to glacial landforms on Earth. These features indicate that ice once moved slowly downhill, deforming over time under its own weight and transporting rocky debris along its surface. Radar and thermal measurements show that many of these formations still contain large volumes of water ice beneath their protective coverings, preserved for millions of years in Mars' cold, dry environment. In some regions, the ice is insulated by only a thin layer of dusty regolith, which reduces sublimation and helps keep the deposit stable over long time scales. The shapes and distribution of these landforms suggest that past climate cycles, driven by shifts in Mars' axial tilt, allowed snow and frost to accumulate far from the poles. Over time, this material compacted into glacial ice that crept across slopes and valley walls, reshaping broad parts of the mid-latitudes. Today, these frozen remnants serve as climate archives, revealing that water ice was once far more widespread. Studying them helps scientists reconstruct long-term climate shifts and identify accessible ice resources for future exploration. Much of Mars' surface is shaped by permafrost, ground that remains frozen year-round and contains significant amounts of subsurface ice. One of the clearest indicators of this ice-rich terrain is the widespread presence of polygonal ground patterns. These geometric networks of cracks form as the soil repeatedly expands and contracts with seasonal temperature changes. As ice beneath the surface shrinks during colder periods in response to warming, the ground above fractures into polygon shapes remarkably similar to those found in Arctic and Antarctic permafrost on Earth. These polygons range from small, tightly packed cells only a few meters across to vast networks stretching for kilometers. Their size, spacing, and shape provide clues about how deep the ice lies and how long the terrain has remained frozen. In some regions, troughs bordering the polygons deepen over time as sublimation slowly removes ice from just below the surface, causing gradual collapse. In other areas, seasonal frost collects along crack edges, revealing that the surface still exchanges moisture with the atmosphere. By studying polygonal terrain, scientists map where shallow ice is concentrated, identify regions shaped by freeze, thaw-like stress cycles, and reconstruct the climatic conditions that preserved frozen water across Mars' mid- and high-latitude landscapes for millions of years. Winding across Mars' ancient highlands are vast networks of valley systems, sinuous, branching channels carved into the rock more than 3.5 billion years ago. These valley networks are among the strongest indicators that Mars once supported sustained surface water flow, not just short-lived floods or isolated melting events. Many resemble terrestrial drainage systems, complete with tributaries, branching patterns, and gently curving channels that suggest long-term erosion by running water. Their distribution and geometry imply that early Mars had an active hydrologic cycle, likely fed by precipitation, snowmelt, or groundwater release, allowing water to flow repeatedly across the surface. Some valleys extend for hundreds of kilometers, linking upland terrains to low-lying basins and crater lakes. Others contain terraces, sediment benches, and streamlined features that form when water persists long enough to transport sediment and reshape terrain. High-resolution orbital imagery also reveals fan-shaped deposits where rivers entered standing bodies of water, consistent with sustained sediment transport and long-lived basin environments. Together, these valley networks point to a time when Mars had a denser atmosphere and warmer conditions capable of supporting liquid water across wide regions. By mapping their structure, age, and distribution, scientists reconstruct the planet's early climate and identify ancient landscapes that may once have been habitable. In several high-latitude regions on Mars, erosion has carved steep scarps that reveal thick, nearly pure water ice just beneath the surface. These striking blue-toned cliffs, first identified in high-resolution orbital images, provide a rare glimpse into the planet's frozen subsurface. The exposed ice sheets can extend tens of meters below the topsoil, forming vertical walls that reflect ancient cycles of snowfall, deposition, and long-term climate change. Their clarity and brightness suggest that the ice is remarkably clean, containing only thin layers of dust accumulated over thousands or even millions of years. These ice cliffs survive because the Martian climate is so cold and dry that sublimation, the direct transition from ice to vapor, occurs slowly, even when the ice is exposed to sunlight. As erosion gradually strips away the protective debris above them, new icy surfaces become visible, offering scientists fresh clues about Mars' hydrologic past. Measurements of their thickness, altitude, and orientation help researchers map the distribution of shallow ice deposits across the planet. For future explorers, these cliffs represent not only valuable scientific archives, but also accessible reservoirs of water, one of the most essential resources for sustaining human presence on Mars. One of the most debated ideas in Martian science is the Northern Ocean hypothesis, the proposal that Mars once hosted a vast ocean covering much of its northern lowlands. The planet's topography provides a major clue. The northern hemisphere lies several kilometers lower than the southern highlands, forming a broad basin known as the Northern Plains. This elevation difference suggests that if large volumes of water were present on early Mars, they would naturally have collected in the north. Along the boundary between the highlands and lowlands, scientists have mapped long, curving ridges and terrace-like features that resemble ancient shorelines preserved in the rock record. Additional evidence includes sediment-filled basins, possible delta deposits, and enormous outflow channels that funnel toward the lowlands, implying that water once moved repeatedly across the surface. If an ocean existed, it may have formed more than 3.7 billion years ago, during Mars' early history, and could have ranged from short-lived seas to longer-lasting bodies of standing water where sediments accumulated over time. However, the hypothesis remains uncertain. Volcanic resurfacing, erosion, and later impacts have heavily modified the landscape, making shoreline features difficult to confirm. By studying these proposed coastlines and sediment deposits, scientists estimate how much water Mars once held, how its climate evolved, and whether northern seas could have offered habitable environments. On steep, sun-facing slopes across Mars, dark streaks appear seasonally and then fade away, features known as recurring slope lineae or RSL. These narrow markings lengthen downhill during the warmest months and fade as temperatures drop, strongly suggesting a process linked to seasonal heating. When RSL were first discovered, they drew intense attention as possible evidence of flowing liquid water on modern Mars. But further study has revealed a more complex picture. High-resolution imaging shows that many RSL behave like dry granular flows, resembling small avalanches of dust or sand triggered when surface material becomes unstable. In many cases, spectral observations have failed to detect clear signs of liquid water, leading researchers to favor dry mechanisms such as dust slides initiated by warming, wind disturbance, or changes in surface cohesion. However, some RSL sites occur in regions where hydrated salts have been detected. These salts can absorb moisture and may lower the freezing point of water, raising the possibility that extremely salty brines could briefly contribute under rare conditions. Today, RSL remain one of Mars' most intriguing active surface processes, showing that the planet is still changing with sunlight, temperature, and seasonal cycles. Across much of Mars, water ice is not locked deep underground but mixed directly into the soil itself, forming what scientists call icy regolith. In high-latitude regions, shallow disturbances, such as small impacts, surface scraping, or natural erosion, have revealed bright ice just centimeters beneath the dusty surface. This frozen mixture of soil and ice can behave like natural concrete, strengthening the ground while preserving water in a stable state for long periods in Mars' cold environment. Thermal measurements and radar observations show that icy regolith is widespread, extending from the polar regions into parts of the mid-latitudes. Its distribution reflects long-term climate cycles driven by changes in Mars' axial tilt. During colder periods, water vapor from the atmosphere can migrate and freeze into shallow soils, gradually building ice-rich layers that remain protected under dust and debris. In some locations, freshly exposed ice remains visible for weeks or even months before slowly sublimating into the thin air, leaving behind dry, collapsed soil. Studying icy regolith helps scientists understand how water moves between the atmosphere and surface, how ground ice responds to seasonal warming, and where accessible ice may exist for future missions. This frozen soil is a quiet but powerful reminder that Mars still holds significant water reserves hidden just beneath its surface. One explanation for Mars' ancient river valleys is the snowmelt hypothesis, the idea that early Mars experienced seasonal melting of accumulated snow and ice rather than sustained rainfall. In this scenario, a thicker atmosphere and stronger greenhouse warming allowed snow and frost to build up across highland regions during colder periods. Instead of constant warmth, Mars may have cycled between cold accumulation phases and brief warming episodes. When sunlight increased during warmer seasons, volcanic episodes, or shifts in the planet's orbit and axial tilt, surface snow could partially melt. This meltwater then flowed downhill, carving valley networks over long periods of repeated activity. The resulting channels display branching patterns, gentle slopes, and distributed erosion that match repeated meltwater flow rather than sudden, catastrophic floods. Climate models suggest that even short-lived seasonal melting, occurring year after year, could generate enough liquid water to shape the observed valleys, especially on sun-facing slopes where temperatures rose highest. Importantly, this process would not require Mars to remain warm continuously, only warm enough at certain times to allow surface ice to melt. The snowmelt hypothesis helps reconcile strong geological evidence for flowing water with the difficulty of sustaining long-term warm conditions on early Mars, offering a plausible pathway for shaping the planet's ancient landscapes. In several regions on Mars, distinctive mineral deposits suggest that groundwater once rose from below the surface and interacted with surrounding rock. These features often appear as bright mineral-rich zones, layered sediments, and sometimes ring-shaped patterns formed as subsurface water seeped upward through fractures and porous ground. When this groundwater reached the surface, it evaporated in Mars' cold, dry environment, leaving behind concentrated chemical residues. Spectral measurements from orbit reveal sulfates, carbonates, and other salts, minerals that commonly form when water evaporates over time. Unlike river or lake deposits, these formations do not require flowing surface water, making groundwater upwelling a strong explanation for mineral-rich terrains found far from obvious channels. Some deposits occur in crater floors and low basins where underground water could collect and periodically rise. Studying these patterns helps scientists reconstruct hidden hydrologic systems and suggest that liquid water may have persisted underground long after Mars became too cold and dry at the surface. Scattered across Mars are hundreds of impact craters that once held long-lasting lakes, providing some of the clearest evidence that liquid water was stable on the planet's surface billions of years ago. These crater lakes formed when water from rainfall, snowmelt, or groundwater inflow collected within enclosed basins, sometimes persisting for thousands, and in some cases possibly much longer, depending on climate conditions. The geological signatures they left behind are striking. Terrace-like features along crater walls, finely layered sediments on basin floors, and fan-shaped deltas where rivers once entered standing water. Many crater lakes show no obvious outlet channels, meaning water remained trapped rather than draining away quickly, supporting the idea of sustained surface water rather than brief flooding events. In several craters, stacked sediment layers reveal repeated cycles of filling, evaporation, and refilling, recording shifting climate conditions over time. These ancient lakes would have offered stable chemical environments where minerals formed, sediments accumulated, and organic molecules could potentially concentrate and be preserved. By studying crater lakes, scientists reconstruct Mars' early hydrologic system, track how climate changed, and identify the environments most likely to have supported microbial life in the planet's distant past. Across many regions of Mars, light-colored mineral deposits mark places where water once pooled and then slowly vanished. These deposits, known as evaporite minerals, form when briny water evaporates and leaves dissolved salts behind. Sulfates, chlorides, and other salt compounds have been detected from orbit and on the surface, often concentrated in ancient basins, crater floors, and layered sedimentary terrains. Their presence indicates that water did not disappear suddenly, but lingered long enough to concentrate minerals through repeated cycles of evaporation. Some evaporite deposits occur in thick, laterally extensive layers, suggesting long-lived lakes or shallow seas that gradually dried over time. Others appear as patchy crusts or bright streaks, pointing to groundwater that reached the surface and evaporated in place. These minerals preserve a chemical record of Mars' changing climate, revealing shifts from wetter to increasingly arid conditions. On Earth, evaporites often trap organic material and microbial textures, making their Martian counterparts especially valuable targets for exploration. By studying evaporite minerals, scientists gain insight into the chemistry of ancient Martian waters and the processes that transformed a once wetter planet into the dry world we see today. Hydrated silica on Mars provides some of the strongest evidence for long-lasting interactions between rock and water. This mineral forms when volcanic materials are altered by liquid water, often in environments where water remains present for extended periods rather than evaporating quickly. On Earth, hydrated silica commonly develops in hydrothermal systems, hot springs, or persistent lake margins, settings known for their chemical stability and potential habitability. On Mars, bright silica-rich deposits have been identified in ancient terrains, including crater floors, fractured bedrock, and regions associated with past volcanic activity. Their chemical composition suggests formation in neutral to mildly acidic water, conditions far more favorable for preserving organic material than harsh acidic environments. In some locations, hydrated silica appears finely layered or concentrated along fractures, indicating repeated water exposure over time. Because silica can trap and protect biological signatures for billions of years, these deposits are among the most promising targets in the search for evidence of past life. Studying hydrated silica helps scientists reconstruct Mars' hydrothermal history and identify environments where water, heat, and chemistry once combined in stable and potentially life-supporting ways. In some of the coldest and most isolated environments on Mars, water ice has remained locked in place for astonishing spans of time. Along steep crater walls, deep pits, and sharply sloped depressions, especially near the planet's poles, there are regions that never receive direct sunlight. Because Mars has only a slight axial tilt and a thin atmosphere, these permanently shadowed areas stay extremely cold throughout the year, with temperatures so low that ice cannot melt and barely even evaporates. Orbital spacecraft have captured striking images of these zones, revealing bright, reflective layers of water ice exposed just beneath a thin covering of dust. In some locations, ice can be seen directly on cliff faces, suggesting it was uncovered by erosion or landslides. Radar instruments orbiting Mars have gone even further, showing that these icy deposits can extend several meters, and in some cases tens of meters, below the surface. The surrounding rock and constant shadow shield the ice from solar heating, keeping it remarkably stable. This stability is important because ice elsewhere on Mars behaves very differently. At lower latitudes, ice slowly sublimates, changing directly from solid to vapor, and is lost to the atmosphere over time. In contrast, ice trapped in shadowed regions remains largely unchanged, preserving a valuable record of Mars' ancient climate and water cycles. Similar cold trap environments on the Moon show that darkness alone can protect ice for billions of years. On Mars, these hidden reservoirs help scientists trace how water moves across the planet and highlight some of the most reliable natural sources of water for future robotic and human exploration. At Mars' north and south poles rise enormous domes of ice and dust known as the polar layered deposits, some of the most detailed climate records in the entire solar system. These vast formations consist of alternating layers of water ice, frozen carbon dioxide, and fine dust, slowly built up over millions of years. Each visible band represents a shift in Mars' climate, caused by long-term variations in the planet's orbit, axial tilt, and distance from the Sun. When Mars' tilt increases, polar ice becomes unstable and can slowly migrate toward lower latitudes. As the tilt decreases, colder conditions return, allowing ice to accumulate again at the poles, while dust settles between layers. Over repeated cycles lasting hundreds of thousands to millions of years, this process creates the striking stripe patterns that are visible even from orbit today. Radar observations reveal that these deposits are several kilometers thick and contain vast quantities of frozen water. Enough that, if melted, they could dramatically reshape the planet's surface. By carefully studying the layers, scientists can reconstruct Mars' ancient climate cycles, track long-term changes in its atmosphere, and understand how water has moved across the planet over time. These icy archives provide an unprecedented window into the red planet's environmental history. Some of the largest channels on Mars were carved not by slow, winding rivers, but by sudden and catastrophic floods that reshaped entire regions in a geological instant. These ancient outflow channels stretch for hundreds, and in some cases thousands, of kilometers across the Martian surface, with widths comparable to Earth's largest river valleys. Their immense scale indicates that staggering volumes of water were released in a very short time, likely when subsurface ice melted or when pressurized groundwater violently broke through the planet's crust. Unlike familiar river systems on Earth, these channels show very little branching. Instead, they are marked by streamlined islands, deeply scoured bedrock, and long, parallel grooves etched into the surface, landforms that can only form under extremely fast, high-energy flows. Many of the channels begin near regions known as chaotic terrain, where the ground appears collapsed and fractured, signaling locations where vast underground reservoirs suddenly emptied. Scientists believe these megafloods occurred billions of years ago, during periods of volcanic heating or major climate instability that destabilized buried ice and groundwater. Although the floodwaters vanished quickly, the channels remain as dramatic scars across the Martian plains. By studying them, scientists uncover how Mars transitioned from a wetter world to the frozen desert we see today, and how liquid water once surged across its surface with extraordinary force. The valleys, deltas, and frozen reservoirs scattered across Mars reveal the traces of an ancient hydrological past. Long before this planet became the silent desert we see today, water likely shaped its surface, carving channels, filling impact basins, and leaving behind the outlines of lakes that vanished billions of years ago. Yet water does more than shape landscapes. It leaves chemical fingerprints, preserved within rock. Across Mars, layers of stone form a vast geological archive. Minerals created in water, volcanic plains forged by ancient eruptions, and sediments recording environmental conditions from a distant era in the planet's history. To truly understand Mars, we must read the story written in its geology, because the water may be gone, but the rocks of Mars still remember everything. Coming next, Part 3. Geology, Rocks and Minerals.